Welcome, and thank you for joining today's seminar on SoundCheck virtual instruments. Topics for today's presentation on virtual instruments in SoundCheck include what are virtual instruments and how to use them in SoundCheck. We'll look at how instruments use existing SoundCheck signal paths and calibrations. We'll tour the individual instruments. We'll show you how you can use multiple instruments and save virtual instrument configuration files or .vic files. We'll explore using virtual instruments in a SoundCheck sequence. We'll demonstrate practical applications of SoundCheck virtual instruments. SoundCheck's virtual instruments, or VIs, are software-based versions of their hardware counterparts and have been an integral part of SoundCheck since 1997. They can be used as standalone instruments for quick measurements or incorporated into a test sequence. Virtual instruments are accessed from SoundCheck's Instruments menu and include a signal generator, multimeter, oscilloscope, spectrum analyzer, multi-channel RealTime analyzer, distortion analyzer, and frequency counter. A strip chart recorder can also be added to display measurement over time to the multimeter, distortion analyzer, and frequency counter. If an instrument is not accessible from your menu, you may not be licensed for it. Contact your Listen sales engineer or rep, and we'd be happy to help you. Virtual instruments avoid the need for additional standalone laboratory instrumentation, saving money and ensuring that all your instrumentation can travel on your laptop. And unlike hardware instruments, software virtual instruments can be updated and improved with relative ease. Virtual instruments in SoundCheck use existing signal paths and calibrations, and this ensures confidence in your measurement, but also ensures that your units of measure are pertinent to the chosen signal path. Let's look at that in SoundCheck. I will open up a signal generator. Okay, and you'll see I'm just generating a sine wave at 1K through the output signal path, which is amplifier, and the level is represented here in volts. If I switch the signal path and I choose a mouth simulator, for example, now you'll see that the units of measure are updated to a pertinent unit of measure for a mouth simulator, which is in Pascal. Multiple iterations of each instrument can be opened simultaneously and configured independently. An entire set of instruments and all their settings can be stored to a virtual instrument configuration file or a .vic file. Configurations can be reopened and even enabled at startup, and gain settings are available on input virtual instruments that can change listen hardware input gain on the fly. So let's look at that in SoundCheck. I'm going to create a virtual instrument configuration file. I will open a signal generator and I will open a multimeter. Okay, I'm outputting to my amplifier. I'm going to input from my reference microphone. I'll view this logarithmically. And if I unmute, now suppose I want to save this as a configuration file that I want to reopen as a signal test. All I would do is go to my Instruments menu and save the configuration. And I might name this Signal Generator Multimeter. Okay, and the beauty here is that all of the settings that I have in these instruments will be saved, and if I close, I can easily reopen that saved configuration file. So I can also force this virtual instrument configuration to load up at startup. So perhaps before I start my measurements during the day, I want to do a quick signal test, and when I launch SoundCheck, in the launch startup, down here I can choose a virtual instrument configuration to load at startup. Gain settings can also be adjusted on the fly. In my multimeter, you see my input signal path is the reference microphone. To the right of it, I have a gain drop list. Currently, I'm auto-reading any dynamic changes to gain on the instrument, But if I drop this list, I can also force any kind of gain change on that input signal path. Okay, let's take a look at the individual instruments, starting with the signal generator. Typically in a signal generator, I could output a fixed tone and level. So here I have a sine wave. I'm going to change the signal path to output to my amp channel. I'm going to increase the gain here to 100 millivolts. Okay, and exactly what you would expect if I play. There's my 1K tone. Okay, and the signal generator can support not just fixed sine waves, but if I drop this list, you'll see I have available pink noise, I have white noise, and I have wave files available as well. Let's look at the pink noise signal generator. When I choose pink noise, you'll see I am generating pink noise between the frequency of 20 to 20 kilohertz, and I can even create band limited pink noise. So let's say I only want pink noise from 100 to 10K. Now I have band limited pink noise. Let's play that back. Okay, down here I have play modes, and I could play for a continuous loop, a fixed duration, let's say 4 seconds, or n number of times. So I could type in 100 times, play back that pink noise. Okay. Also available, I could play back wave files, or I could play back SoundCheck waveform files. Let's look at a wave file. Here is the directory of default wave files that we install with SoundCheck, and I'll just open this ITU Real Speech wave file. Okay, let's play that back.
The shelves were bare of both jam or crackers. A joy to every child is the swan boat.
The stems of the tall glass.
Okay, you'll see that we'll indicate if this is a mono stereo with the sampling rate and the sampling format is here, as well as I could set a length that I want to play that wave file. So I could tell here that this is about a 13-second wave file. Perhaps I only want to play 4 seconds of that in a continuous loop. And here we go.
The shelves were bare of both jam or crackers. The shelves were bare of both jam or crackers.
Okay, so that's a continuous loop of just a section of the wave file. Other applications of this is, as I said, we can load in SoundCheck waveforms. So perhaps I do an acquisition and I have a recorded waveform. If I want to play that back, anything that's a waveform in my SoundCheck memory list, I could load as a waveform, play that back, and audibly hear the recorded waveform. And that's really useful if you want to audibly correlate maybe your measurements with maybe audible defects. Okay, and you'll also see in the signal generator, there's an EQ checkbox near the signal path. And if I have a signal path like a mouth simulator or a source speaker that I've previously calibrated, and by calibrate, I mean I've measured the speaker's response, I've come up with a correction curve to flatten the response of the signal path. Checking this box will apply the correction curve to the wave file's output, thus reducing the speaker's own response from the playback. Okay, next up is the multimeter. And to demonstrate the multimeter, before I do that, I'm actually going to open up all the meters in SoundCheck, which include the frequency counter and distortion analyzer. To do that, remember, I could save previous virtual instrument configuration files, and I saved a meters VIC file. And so you'll see the multimeter on the left, distortion analyzer in the middle, and frequency counter on the right. And really, I want to draw your attention to the tabs in these windows. Okay, the tabs are pretty consistent, at least the first 3: measurement, average, filters, and limits. So I'll show you that in the multimeter. The distortion analyzer has an additional distortion tab, which I'll talk about when we get to that instrument. So just bear in mind that's consistent across the 3 meters. One other thing I'll point you to in the instruments is that we could have a collapse view. So once we set up our instrument, if we want to keep an instrument running, if I click this collapse icon, I can have sort of a condensed view of the instrument. Okay, so this is the multimeter, and you'll see that I have a running update of signal at the microphone reference position. Maybe to demonstrate that, I'll actually open up the signal generator, and I'll just output some kind of signal. I'm going to output to the amplifier and maybe bring up this level to about 100 millivolts. So 1K tone, what you'll see is an update at the in the meter as I play this back. Okay, and what are we looking at? The meter is giving a running update, and I can do a measurement type. Right now I'm doing RMS, acoustic, but I could do peak. If I had some kind of DC electrical input, maybe an interface that had DC coupled input, I can also measure DC. Here is the signal path for the measurement. Okay, and as I showed you earlier in the presentation, I can monitor or adjust the gain on the fly for that signal path input. Okay, now if I scroll across, this tab will show what kind of averaging I could do. I could do linear repeating. In this case, I'm doing a continuous moving average. Okay, and also what is the time weighting? If I drop this list, I could do a fast, slow, or a user-defined weighting. The next tab is where I can define, perhaps I want to have a high pass or low pass filter. Maybe anything below 20 hertz or above 20 kilohertz is not factored into the measurement. So I can enable the high pass, low pass filter here, or maybe I want to apply some type of weighting. For example, a weighting on input. Now that measurement is averaging at a weighted scale. Okay, then lastly, on the right side, I can set limits. So if I want to have a running limit above and below my input signal, as long as the signal is within the above and below limits, I could set that up as well. Okay, so that is the multimeter. Next up is the high resolution frequency counter, which offers an accurate and clear visual indication of frequency, determining the dominant signal in a selected signal path, and it returns a precise frequency measurement. Let's open it up. Okay, and this looks very much like the multimeter that we saw previously, same tabs, but here I have a running update of the input frequency. I'm outputting 1K, so let's just look at that. Okay, most importantly here is not only can I determine frequency, but I can monitor at a very high level of precision. So if I right-click, you'll see that I can control how many digits of precisions and trailing digits I want in the measurement. Fairly straightforward, but that's the high-resolution frequency counter. This is useful for calibration, maybe calibrating an audio meter for testing playback systems to ensure that they're playing back audio at a constant rate, and for any other application requiring high-precision frequency measurement. Next up is the RealTime Distortion Analyzer, and this offers a real-time reading of distortion at a single frequency in real time. The benefit of this in a virtual instrument is that we could perform distortion measurements on the fly without having to create a test sequence with an acquisition step and an analysis. So if you look at the far right-hand tab, I have a distortion tab, and this is where I would select the harmonics that would be factored into the THD percentage measurement. Okay, if I click back to the measurement tab, you'll see I have a drop list here of different distortion measurement types. These are the same analysis that we perform in a distortion analysis step in SoundCheck, which include THD ratio, that's IEEE and IEC, residual, THD plus N, IEEE and IEC, as well as SINAD. Okay, so these are the options. And let's just look at real quickly. I'm just going to play a single tone from the speaker to the microphone. Okay, so very good speaker, very low noise distortion. So that is the distortion analyzer. Next up is the oscilloscope and spectrum analyzer instruments. From the instruments menu in SoundCheck, they look like two individual instruments, but they are actually one and the same, and I'll show you what I mean. Here we're looking at the oscilloscope, and from this drop list at the top, I could drop and see that I am currently in the time domain. The x-axis of this instrument is time, and I can easily switch this to the frequency domain. In that case, I am in the spectrum analyzer. But let's look at the oscilloscope to start. Here I'm just doing an exponential averaging, and I will play a single 1K tone. Okay. I could also set this up, as you see on the right. I could set some level for input triggering, so the instrument only triggers on some type of signal input. Okay, so this is the scope. Let's switch over to the spectrum analyzer. Okay, and again here, now my x-axis is changed from the time domain to the frequency domain. Let's just look at that really quickly. I'll play a 1K tone. Okay, and you'll see that here is the peak of the 1K tone. I can snap this cursor to max, and you'll see up top here at 1K, my estimated level is about 74 dB. I can also enable this harmonic cursor. Okay, and the harmonic cursor will indicate where the second, third, fourth harmonics are. And maybe I want to measure the delta between the peak and the second harmonic. So I grab this second cursor, and you'll see down here at the bottom where the cursor is, I'm getting a running delta of the difference between the peak and the second harmonic. The spectrum analyzer uses constant bandwidth FFT analysis. If you look at the right side of this window, I can drop this list and choose the type of windowing I'd like to perform on the measurement. And then below that, I can even apply any type of weighting, A weighting, for example. Okay. Down here, very much like the oscilloscope, I can set some type of input trigger level so the measurement only occurs on an input trigger. And then down here is where I could choose whether I'm doing exponential or linear averaging. Other nice things that I could do here is I can save the measurement directly out of the instrument. So I'm going to do that as a demonstration. I'm going to hit play here. And you see the save to memory list. I will click the button. And let's look at that. That was saved to SoundCheck's memory list. There's the spectrum, and if I double click the spectrum, there's the FFT analysis captured on an XY graph. Okay, so that is the spectrum analyzer. So next up is the strip chart recorder module, and this expands the capabilities of your meters, specifically the multimeter, distortion analyzer, and frequency counter in SoundCheck. This adds the ability to plot the measurement over time. And think about it in the legacy days of having electronic equipment with a paper strip chart recorder. So we're adding measurement over time to these instruments. Let's demonstrate that. I'll open up the multimeter. Okay, and as I said, this is an add-on option in SoundCheck, and if the option is added, you'd have an icon that allows you to display the strip chart recorder. So you'll see I have a running update on the right side, and I can view that running update as relative to when the instrument opened, or I could view in actual local time. Okay, so that is the x-axis, and let's just play back. Okay, and as I increase the level here, the strip chart recorder updates accordingly. So this would be very useful in an environment in any of the meters where you have to measure over time. If a monitoring level, for example, I may start a test overnight and look for any dropouts potentially in the signal, or if there are level changes that should not be in a constant signal. Other things that I could do with the strip chart recorder, very much like any of my other instruments, I could save to memory, And if I save to memory, this curve would be saved to the memory list, where the x-axis now is time and the y-axis is the measurement itself. So that is the strip chart recorder. One other thing I will show you is the instrument the strip chart recorder can be separated from the instrument. So perhaps I want to expand the strip chart recorder, maximize it, okay, and then I could pop it back onto the instrument. Okay, that is the strip chart recorder. It's an add-on. It adds time measurement over time to any of your meters in SoundCheck. Next up is the MultiRealTime Analyzer, or RTA, and this enables a signal to be analyzed using constant percentage bandwidth filters. And this is different from constant bandwidth FFT analysis and better correlates to human hearing. The filtering continuously analyzes complex signals such as speech, music, and pink noise, and it's widely used for telephony applications and measuring ANC headphones. SoundCheck's RTA offers true recursive digital filtering conforming to the ANSI standard. Analysis options include various octave bands up to 24th octave. Okay, so let's look at the multi-RTA. Currently, I have the instrument open, and you'll see I'm monitoring 2 input channels. Each input, as I click on it, has settings below. This defines what my signal path is, how I'm averaging, what my octave resolution is, and weighting. I can save each input with unique settings, and I can add as many inputs as I want by clicking the plus symbol at the top, and you'll see I have RTA. Additionally, I can perform calculations by adding a calculation into the RTA. So for example, if I wanted to power average multiple inputs, I could choose power average, but I could also do other calculations like subtraction, maximum, and minimum. Okay, so for the purposes here, I'll just choose power average, and you'll see down below I can engage which inputs I want to factor into that power average. And when I do that, you'll also see that a unique curve with color appears on the left-hand side. So like any of my other instruments, I could save these spectrum to my memory list for use later. So that is the multi-RTA in SoundCheck. Okay, I'd like to demonstrate a practical use of using SoundCheck virtual instruments in SoundCheck. As I mentioned before, I could save virtual instrument configuration files, and to demonstrate this, I'm going to open a previously saved VIC file. If we look at what's open, I have 3 instruments open, and I'm going to do a level and balance test on these headphones that I have on my mannequin. On the left side, you'll see I have 2 signal generators, and I'm just generating pink noise to the left ear and the right ear of this Bluetooth headphone. Now, one of the things that you'll notice in the signal generator, when I have multiple signal generators open, I have a synchronization or a sync checkbox up here in the top. And this will perform simultaneous playback of the stimulus and perfect sample accuracy. So the left and right side are getting the same pink noise to the sample. Once I play to the headphones, what you see on the right side is I'm going to capture the RTA spectrum of the ear simulator inside of the mannequin through the left and right ear. And that's what we're looking at right now. Here is the settings for the left ear. Here are the settings for the right ear. Okay, so this is a 6th octave resolution. Let me just hit play and you'll see the spectrum in my display. Okay, notice when I hit play, both signal generators unmuted, and I have reasonable balance here. This is actually a pretty good fit of the left and right headphones. So prior to doing a test sequence, I may want to do a balance test using a virtual instrument configuration very much like this. So this will tell me not only is my left and right balance, but perhaps my positioning on the ear is not so good. So if I had a leak, you'll see what happens to the right ear in this display. Okay, so Practical use, once I have a good balance of the left and right ears, then I can close this instrument and perform a sequence that measures the headphone. Okay, so that is using a virtual instrument configuration, multi-channel RTA, feedback in real time, 2 synchronized signal generators generating pink noise. Next, I'd like to demonstrate the practical use of using the multi-channel RTA measuring input from a 6 microphone array. The 6 microphone array can be used in a automotive tuning application, and the idea is that the position of the microphone gets placed at the approximate position of the head in the driver's position, and the vehicle can be tuned in real time, power averaging the 6 microphones to a target response. So what we're looking at on screen is a multi-channel RTA, and you'll see that I have 6 RTAs configured for 6 inputs. And then here I have a calculation, and this will power average all of the 6 microphones. Okay, what I'll do is I'll generate some pink noise. Okay, and then you'll see that the 6 microphones have settled, and that's the approximate tuning of the head position. Now, if I had a golden reference target on the in my memory list, I could drag that into the graph on the left side, and an engineer can tune the DSP inside of the vehicle to best meet that target curve. Okay, so again, this is a 6 microarray using a power average calculation. Typical application is tuning an automotive in-vehicle from the head position. So up to this point, you've seen examples of using virtual instruments in SoundCheck, both as individual measurement tools or in combination using virtual instrument configurations. SoundCheck can further augment the power of virtual instruments by incorporating them into a test sequence. On screen, I have a very simple example of a virtual instrument sequence, and this is using a virtual instrument acquisition step. So on the left side of my sequence editor, you'll see under the acquisition steps, I have virtual instrument acquisitions. And on the right side, in this very, very simple sequence, I have step number 1 as a virtual instrument acquisition step. And if I open this, you'll see that I have a RealTime Analyzer, this time just a single input. This is on my reference microphone here, and I'm going to measure the spectrum, the RTA spectrum of this fan. This is a time-based measurement, so I'll do a linear measurement for about 5 seconds. Then afterwards, I'll have the spectrum of the fan. Next up, I'll pass that spectrum through a limit step. I have a defined upper and lower limit. And then lastly, I'll plot that onto the XY graph that you'll see on the left side. Okay, great. So let me start up the fan, and I will play this sequence. You see the spectrum. 5 seconds will be captured. And there we have it. Let me stop the fan. So you'll see the spectrum is calculated using a virtual instrument acquisition. I've passed the spectrum through an upper and lower limit. Not very good limits, but you get the idea. SoundCheck can incorporate virtual instruments as part of a test sequence, and this is a very quick and easy example of that. This concludes our presentation today. Hopefully now you can see how virtual instruments can take traditional bench-style measurements and bring them into a software-based test system. Using a program like SoundCheck as your measurement tool is more convenient than bulky standalone hardware instruments. These virtual instruments are fully integrated into your existing SoundCheck test system and available to be used both in standalone mode or within test sequences. If you've seen an instrument in the seminar that's not currently on your license, I encourage you to contact your licensed sales engineer or rep. Thanks again for attending.